Let's welcome Fredrik.
Thank you. Thank you. Let's see. Okay, we're on time. So my name is Fredrik. I go by these avatars on the online platforms. And today we'll talk about discrete time modeling in Modeling Toolkit and whatever that means. All right, so on the screen here I have two groups of emojis. I will try to point. On the left-hand side we have some things that occur in nature. We have a planet, we have a car, we have a funny monkey and so on. And on the right-hand side we have devices mostly. We have a computer, a phone. For the purpose of this talk, these two are the same. We have some currency here. This represents data that we have recorded at certain time points. Okay, so I was limited to whatever is representable as an emoji. We have a clock. There is only an analog clock emoji, but this clock, what is important is that it ticks. And it doesn't obviously tick all the time. It ticks at certain points in time. We also have here is an integral sign, and here is a summation sign, and they will become important. So all of the emojis on the left-hand side have something in common, which is different from what these guys here on the right-hand side have in common. Any takes on what they have in common on the left? Chris, what do they have in common? Their state exists on a continuous timeline. Okay, so from the time this monkey was born, no matter what time point you pick, the monkey has a particular state. All right, but the data here we have recorded for this currency. We recorded that at a particular time and at another particular time, but in between we don't have access to that data. It's not available. All right, so this kind of represents something that happens on a discrete time variable, whereas these are continuous in time. All right, so to illustrate that a bit more, we have a graph. The guys on the left, the continuous time characters, they draw kind of trace out smooth graphs as a function of time. Whereas the guys on the right here, they are defined at particular points in time, and in between they are just not defined. There is no such things as talking about their state at time points in between. All right. And when we model these systems on the left-hand side, the state of the monkey and the basketball player and so on, we might use differential equations. So the derivative of their state, the state here is called x. I'm from control theory background, so we use x for state. It's a function of the current state and some input u and maybe parameters in time. Whereas here on the right-hand side, we also model change in some sense. But we model what is the state at the next time point as a function of the state at the current time point. So k here is kind of a sequence index. So x of k is the x at the current time point, whereas xk plus 1 is then the next state. All right, but what happens then if I draw this diagram? So I have one guy from the left. It's the car. It has a continuous state, position and velocity and so on, angle of the wheels. And then we have a computer, which has a discrete time variable. They don't even have the same time variable. How can we put them in the same diagram? Does that even make sense? And this diagram maybe does not make sense, but we will try to insert some things that make it make sense. So now the diagram has become more complex. We have some graphs also. And what has happened in the diagram is that we have inserted two, I call them operators. So there is a sample operator. So sample means to take a measurement. And there is also a little clock associated with that. So we take a measurement when the clock ticks. All right, and the other operator is hold. So that's a way to interpolate. So we define something at a particular point in time, and then we hold that constant until the clock ticks again. Right, so we will kind of break that down and relate it to the graphs. So if we consider the sample operator, it's a transition from the continuous time domain to a discrete time domain. And I say a discrete time domain because there might be multiple different discrete time domains. Because we might have multiple different clocks in a system. And in a model. So on the left-hand side, maybe I will try to point with a pointer instead. Let's say we have the car. It has an acceleration profile. So this is my mother driving. She pressed the gas and the brake and the gas and the brake, and your head goes like this. But it does so continuously. All right. And then we insert a sample operator. So we take a measurement of what is going on here, maybe using an accelerometer. And we do that when the clock ticks. And the clock here maybe belongs in a computer or some electronic device. And then we get a sample, a measurement, and that is represented here in orange in this curve. But then it takes a while until the clock ticks again, and we have no clue in the discrete time world what happens in between there. We are certainly not having a constant acceleration in between there. So we just don't know is the fundamental aspect. But the continuous time world, of course, still continues to evolve in between there. And when the clock ticks, the computer performs some computation. It's in the nature of a computer. It wants to do that. And it comes out with some output. So this may be a controller for a cruise controller in the car, something like that. And that output is then defined at the clock tick. But we might want to make that available to the continuous time world so it can control the throttle or the brake or what have you, right? And what we do then is we insert a hold operator. So we say that take the last available defined value and hold that constant until something else happens. There are other ways you might interpolate from discrete time to continuous time, but for now we will just stick to the zero order hold. Zero order hold meaning that you hold it constant. It's a zero order polynomial. All right, so how do we model such a system in Modeling Toolkit? We have introduced this little convenience object called a shift index. All right, so here I call the shift index k. I create such an index. You can use this as an argument to your variables. So typically, maybe in Modeling Toolkit, we define variables using this syntax x of t, indicating that x is a function of time. All right, discrete time variables are also defined in the same way. But when we index a variable using the shift index, we have now told Modeling Toolkit that I am now talking about what happens when the clock ticks. Okay, so in the equation I of k is now related to I of k minus 1. So the current value of I is related to a past value of I plus the current value of some other variable e here. And then I use the sample and the hold operators to transition between time domains. So on the right-hand side here, I have a model. I hope it's large enough for you to see there. It's a regular Modeling Toolkit model using the macro syntax. I start by creating this little shift index here, and then say at mtk model, my discrete model. I define some variables. It looks exactly the same as it does for continuous time systems. I have some parameters, and then I have equations. And I have split the equations into two groups here. But my splitting into groups is only using comments, so Modeling Toolkit doesn't actually care about that splitting. I have 3 equations related to a car. Okay, it's a very simple first-order car. And we see the first equation says that u, there is a variable called u, is equal to hold of ud. All right, so I haven't said what is continuous and what is discrete here. But Modeling Toolkit is smart, and there is some information in this hold operator. All right, so Modeling Toolkit knows that you can only hold discrete time variables. So therefore, UD must be discrete time. And the result of holding a discrete time variable is a continuous time variable. So U must be continuous time. So even though I haven't said what is continuous and discrete, Modeling Toolkit will figure it out based on how you use it. And if you try to use a variable so it's ambiguous, whether it's continuous or discrete, you will get an error saying that I can't figure out what the time domain of this variable is. All right, and the bottom few equations are related to a controller. It's a simple PI controller. And it starts by sampling the continuous time variable y with a particular sample interval ts. All right, and then that produces a discrete time variable yd. And then I can use that to perform computations. And perhaps the interesting part here is the integration. And in discrete time, integration translates to some form of summation. So the integral state, I, at the current time step k, is a function of the integral state in the past time step, k minus 1, plus the error. Okay, so that's just the basic integration equation in a PI controller. And so on. All right, and if we simulate that, we get the little step response. All right, so I've been talking loosely about clocks and clock ticking and so on. So shall we go into a bit more detail what that means? A modeling toolkit model that has a discrete time part, all right? Each discrete time part is associated with a clock. You can create clocks yourself using the clock constructor, but typically you don't have to even do that. When you say sample this variable at a particular sample interval, a clock is created underneath the hood, so you don't even have to create it. But each clock, what it does is that it ticks, all right? And it ticks at certain time points. The default clock is periodic, so it ticks with a certain interval, and that interval is always the same. You can also have a clock with some random jitter in it. Maybe that corresponds to something happens when you receive traffic over the network, and networks are unreliable, so sometimes it takes slightly longer and sometimes slightly shorter and so on. Or you might have an event clock, so maybe when a ball bounces, a clock ticks. Okay, so that doesn't sound like a clock, but it's kind of a generalized clock. It's something that ticks at least. And yeah, I said you can construct them, but you don't have to. So the next step a modeling toolkit does when you have provided it with a model is that it performs clock inference. So I already alluded to what that means. It's essentially a modeling toolkit looking at all your equations and saying, UD appears inside of a hold. That must be a discrete time variable. And that must result in a continuous time variable. And the differential operator here, D, it also holds similar kind of information. We know that we can only apply a differential operator to a continuous time variable. So therefore, X must be continuous time. Y does not have any such information associated with it, but Y appears in an equation together with X. So therefore, this equation must be a continuous time equation, and therefore Y must also be a continuous time variable. So modeling toolkit does this for you, and this is what we refer to as clock inference. We infer the clock, or if it belongs to the continuous time domain, for each variable and for each equation. And the result of that is a list of clock partitions. So it's variables and equations that are associated with each clock, plus the continuous time domain then. And modeling toolkit uses all the operators and the shift index to figure out which partitions variables and equation belong to. And as I said before, the transition between time domains is done by hold and sample. And there is actually yet another operator, it's called clock change, because you can transition between two different clocks. For instance, if you want to supersample a variable, subsample a variable, shift the phase of a variable, but maintaining the tick interval and so on. You can all do all these things. I've spoken about this. All right, the next step modeling toolkit does after figuring out the clocks is code generation. So the continuous time domain results in an OD, just as you are used to in modeling toolkit, but each clock partition results in a discrete time callback. So it's something that is called at a particular time point. You run a computation, update maybe state and parameters, and then the simulation continues. So a little detail there underneath the hood is that the discrete time state is in modeling toolkit and differential equation stored in the parameter object. So the parameter object in modeling toolkit has been expanded into its own custom data, like a struct that maintains what you consider to be the parameters of the system, but also the discrete time state. The key thing is that it's not part of the continuous time state, so it's not what the OD integrator needs to be concerned with when it performs the integration. All right, so how do we implement generic discrete time components in, for example, a model library? So in modeling toolkit standard library, we have things like integrator, derivative, transfer function, state-based object, and stuff like that. And we can create such a standard library for discrete time components also. But when we do that, we don't want to make a choice of a clock, because the user is supposed to choose the clock and the sample interval and so on. But we might still want to be able to refer to aspects of that clock. For instance, what is the period of the clock? So here we see an example. It's the standard library definition of a discrete derivative. When I say discrete here, it should always be discrete time. So it's discrete time derivative. And we see that a discrete time derivative is like a finite difference, right? It's the difference between two values. It's the difference between the value of u at the current time and the value of u at the time point before, divided by the duration of the sample interval. But we haven't specified what the sample interval actually is here. And that's where clock inference comes in again. After Modeling Toolkit has figured out this component is used with a certain clock, that clock is specified externally to the component, but grab the sample time and put that into the variable TS and then use that in this equation. All right, and I can just share a bit of best practices I've figured out while implementing this standard library. We see that I have a block here called structural parameters. So these are not parameters in the Modeling Toolkit sense of a parameter. Instead, they are more like function arguments when you create the system. It allows you to modify some aspect of the equations. And I include both the sample time and the shift index as structural parameters with defaults. So if the user just instantiates a discrete time derivative without specifying those, the defaults will be used. But this also gives the user the ability to override the sample time, should they desire to do that for various reasons. Or be able to overwrite the shift index by providing a specific clock to choose a point in the model at which to specify the clock. If you don't use that, the clock is inferred based on the context. How is this component used together with other components? Key is that the clock is specified somewhere in the model, but only at one location. All right. Can we have multi-rate systems? Yes, we can. I have alluded to that before. We can have a system that includes many different clocks. So here we have a very similar system to the one before. But I have created two variables here at the top, TS1 and TS2 for two different sample rates. And then we see down in my controller, it now says sample Y with an interval of TS1, all right, and sample Y with an interval of TS2. All right, TS1 and TS2 are different, so this creates two different clocks. And then we perform some computation using the sample values. And we see the result of simulating that on the left. And I've indicated the clock ticks here with dashed lines, and they are using colors. I hope you can see that. So we have one clock that ticks every 0.3 seconds, and it changes the behavior of the continuous time system in a particular way. But then every 1.1 seconds, the green clock ticks. And then we have a completely different change. So you can do things like multi-rate systems. You can also change the clock of a discrete time variable to a different clock, and you can use this to increase the sample rate or decrease the sample rate, or just change the phase. So here we have an example where we change the phase of a variable. It's a very simple simulation. We just have two discrete time equations and a continuous time equation. And the two discrete time partitions interact through this clock change operator. So we say we have a variable here belonging to clock 2, but we change from clock 2 to clock 1, and it's now available to use in the first discrete time partition. If we hadn't included this clock change operator here, Modeling Toolkit would say clock inference exception. I can't figure out what the clock for X1 is because it looks like it belongs to two different clocks. So you have to be explicit about what is your intention here. All right, standard library. So I have alluded to the existence of such a library. It does exist. It's open source. It's available at the Dinosaur there. It includes things like a delay component. So a delay in discrete time is just a one time step delay, but it's generalized so it can be as many time steps of a delay as you want. There are integrators, which in discrete time is summation, but you can discretize a continuous time integrator in multiple different ways. So you can have a backward discretization, a forward, or a Tustin approximation, and so on. There are derivatives, PID controllers, sample and hold, of course. I show here in gray transfer functions and linear state space objects because they are kind of implemented, but they don't work yet. So, yeah, work in progress. And there are also noise sources. And noise sources in discrete time are easier in some sense than in continuous time. Because in discrete time, when the clock ticks, you just draw a random number, more or less, and then that's your value of the noise. And that's very useful when you simulate things like measurement noise in a sensor. So a sensor is taking a measurement at a particular point in time, and it's always associated with some noise. So we can model that also. So can we do non-trivial things? Yes, we can. On the QR code there is an extension to a tutorial from Modeling Toolkit standard library. It's a DC motor that has a velocity controller. And here I've extended it to also include a position controller. So you can do things like that. And I say here I wanted to actually make this a multi-rate system, but since this is work in progress, that did not work. So now the position controller and the velocity controller are the same. But what we see in the plot here is we have two curves. The blue one is the original tutorial from Modeling Toolkit standard library, where the controller is implemented in continuous time. We have a step response here in the beginning in the reference. Okay, so we have some overshoot, but then it meets the reference. And then there is a step in a disturbance torque after 2 seconds. And the controller, having integral action, it managed to reject that disturbance completely. And when we implement this controller in discrete time instead, with a particular sample rate, we see that there is a slight degradation in performance. We have a slightly larger overshoot, and this disturbance is also slightly larger before it's rejected. And that's kind of expected, right? Because the continuous time controller, it sees the disturbance instantaneously, whereas a discrete time controller, it takes a while before it actually sees the disturbance. All right, so this is very useful to verify that when we have taken our maybe continuous time design of a control system, does it work when we implement it in discrete time? And if it doesn't, maybe we have to do something about that. All right, is there documentation available? And the answer is yes, and kind of. So at the QR code here, there is the documentation, that is available in Modeling Toolkit. It's very incomplete. It just gives you kind of the overall idea, but you can check it out already today. Then there is documentation available in Modeling Toolkit sample data.jl. It's available on GitHub, but it doesn't render because it doesn't actually build yet. So you can read the source files, but it's not going to be very interesting to you, perhaps. But if you're interested in this topic, you can perhaps go and check that repository out, and hopefully within short it will be released. Can you make use of this today? Not really. It's still a work in progress. So I show a dragon here. There are lots of dragons. You're going to get the wrong answer if you don't know exactly where the bugs are. But hopefully within a month or so, you can actually make use of this. And we will have a release, and I will announce it on Discourse and so on when that release is made. It currently requires the proprietary JuliaCon compiler to compile correctly. There is kind of a compiler in Modeling Toolkit, but it will in certain cases give you the wrong answer. So what we have done there is we just give you an error message for now saying that it's not fully supported. But it's still, JuliaCon compiler is free for academic and personal use. So if you belong to the group of academic and personal users, you can already use it for free. There is a standard library package. It's called Modeling Toolkit Standard Library. It's available on the QR code in the bottom there. And it's not released yet, but it's available. And in the end, I would like to acknowledge the people from the Modelica language who have actually done a very nice design. They are in their second iteration of discrete time systems, and we borrow a lot in our design from their second iteration. So if you're familiar with the clocked semantics of Modelica, you will recognize at least a lot of the kind of look and feel. And I would also like to acknowledge Ayush and Yingbo, my colleagues here, who have been working on lots of the implementation that underpins this functionality. And before we end, I would like to make a teaser here. There will be future work. So what you see in the animation on the right is a finite state machine implemented in Modeling Toolkit. That exists already today, but it's still not released. So hopefully within a year or so, we will have that kind of functionality as well. And we see an automatically rendered diagram on the left-hand side of a state machine that have multiple hierarchies. So we have states that internally contain state machines and so on, and you can transition in between them. So there are lots of things happening on this front, and if you are curious, come and talk to us at the Julia Hub booth, or send an email to me, or open an issue and complain about how we have bugs and so on. All right, thanks.
Thank you so much for your talk. And as usual, does anyone has questions? All right, lots of questions.
Hi, thanks for the nice talk. I was wondering, how does it scale, like the clock part? So, say for example, I am building a team of robot soccer players, and I need to simulate 22 clocks, which are all actually ticking at the same time. Will it like make 22 callbacks, which doesn't scale ideally, or does it bundle everything into one callback?
If the clocks are exactly the same, they will be considered part of the same clock partition, and it will result in one callback.
And is it then, if you give multiple things, like equal clocks, but not identity clocks, like different objects but same content, will that also infer?
It determines equality between clocks based on whether their interval and their phase are the same. So you can't have clocks that have the same interval and the same phase, but they are different.
Okay, yeah, that's clear. Thanks.
Hello, thanks for the talk. I have one question. Is it possible inside, I don't know if Modeling Toolkit or this package, to call complex functions with only discrete variables? Because sometimes when you're modeling the sensor output, just the noise is not enough. You have to go through a very complex situation. So is it possible to call this function and assign it to a variable and then go on with the system or not?
Yes, just like in the rest of Modeling Toolkit, you can, if you can't trace through the function with the Modeling Toolkit variables, you can register that as an atom in the language. And then the call to that function will be represented symbolically. And then when you generate the code, the generated code will call the function. Mm-hmm. But the symbolic language will just treat it as an atom that is not to be traced through.
Okay,
yep.
Thank you very much.
Yep.
Thank you. So if I understand well, the shift index will create a relation between indices and the time steps, and,
yes.
and you can use different clocks and custom clocks. So can this be used for event handling? So this is my first question. And my second question is about the solvers. So how the solvers behave when you start having too much of these discrete states?
Yes. The answer to your first question is yes. So I mostly talked here about periodic clocks, clocks that tick with a certain interval. But I alluded to very briefly that you can have something like an event clock, where the tick of the clock happens when a certain event occurs. For instance, if I drop a ball, when the ball hits the floor, that can generate a tick of a clock. And you can use that to do event-based programming. So you can actually, well, I said you could, but in the future, hopefully you can use things like the state machines I have in the animation here to describe things like some continuous time systems require state machines to handle the fact that the dynamics change when something happens. If I have, for instance, two objects like this, they have each have their own state, position and velocity. Maybe they collide in a way that they stick together. After that, you have fewer equations. All right? So that's a little state machine that transitions from being decoupled to being coupled. All right? So today, we can't model that using this functionality, but the idea is to eventually be able to model that kind of functionality as well using this. Yeah. And your second question, can you please remind me?
The solvers.
solvers. Okay, so it uses exactly the same functionalities as if you had written a discrete time callback yourself using the diffeq callbacks library. So the solvers will stop at the tick time. It will launch the discrete time callback, and then they will restart after the callback with a new updated state and parameter vectors and so on. And if you have a lot of these callbacks, obviously that can become expensive, especially if you have a very fast-running controller. Maybe you have a control system that runs on a kilohertz sample rate, but your continuous time dynamics have very slow time constants, so your sample rate is overkill. Then you spend a lot of time and effort actually just running the control system, so that's expensive. In situations like that, it's sometimes beneficial to have two versions of the model, one where you actually have a continuous time controller, so you kind of ignore the discrete time effects, so that the solver can use adaptive time steps to make quick progress in the simulation. And then when you want to analyze the effects that your discrete time control systems have that are different from continuous time controller, then you switch, and then you pay the price to actually run the high sample rate controller. Does that answer your question?
All right. I think this was the last question, and we'll take a break till 11:40, and then we come back here for another talks. Okay, thank you.
Thanks.